Hello, and welcome back. Today we're going to go over what matter is, the things that matter. Okay. In our uh, video today, the objectives are going to be learn about the composition of matter, to learn the difference between elements and compounds, and define the three states of matter. So, why are we doing this? Why does it really matter? Yes. So we're going to learn the particulate nature of matter. Matter has mass and occupies space. Okay. So anything that has mass and occupies space. So that's everything. That's all the stuff in this world, right? That's weird. What is it composed of? Tiny particles called atoms. All right. Some guy, some great guy, Democritus. He proposed that everything eventually, you chop a plum down, eventually you'll get to little tiny particles that are part of the plum. And then if you chop those up, the plum ceases to be a plum. The particles are, who knows? What are they made out of? What is stuff made out of, though? We could say matter has space and it has weight and mass and stuff like that. But what's the mass made out of? E equals mc squared. Clear as mud, right? Energy equals mass times the square of the speed of light, or speed of light squared. So, yeah, that should make sense, right? Energy, no? Okay. All right. Well, energy equals matter. So really we're saying that matter is energy, with some other fancy energy in there, okay. So the energy stored in matter, like there's particles and there's atoms, and then there's particles in the atoms, and we have quarks, and these quarks make up the protons and neutrons, and then we have like leptons, and that's what the electrons are made out of, and they come in like 6 different types, and there's like up, down, sideways, I don't know, weird, not weird. Okay, so essentially though, all of those particles and subparticles and whatever are just energy, like spinning around energy and spinning around in different patterns, and it comes together and forms protons, neutrons, electrons, and those are going to be forming what we call the elements. All right. Atoms, but basically everything's made out of atoms. Everything that has a mass and takes up space and generally tends to form atoms unless it's part of an atom. But the thing is, elements are just saying that there's different types of atoms, and the elements are all those different types of atoms. We have gold atoms, and we have hydrogen gas atoms. As you can see, they're kind of linked together in little pairs, and gold is right next to each other. And certain element, though, contains only one type of atom. Elemental copper, for example, only contains copper atoms, and elemental gold contains only gold atoms. And bonus, what makes atoms of each element different from each other? I don't know if you remember this. I don't know if you have ever taught this. It's protons, folks. It all has to do with the protons. Sure, we got neutrons in there. That's just to help, And we get electrons to balance charges. But the identity of the atom is the protons. But we're going to revisit that later, okay? So, elements, compounds. Bonus. Yeah, compounds are just like elements that have been combined. All right, here we go. 2 or more different types of atoms is going to make a compound. Okay, so anybody remember why are these atoms right next to each other, like stuck to each other? They're bonded, so if they're just floating around, they're not going to actually be bonded unless there's been a chemical reaction to take place to really bond those atoms together. Maybe you've discovered this in your other classes, and maybe you know that electrons are the deal. Electrons are why things are bonded. Electrons are shared. Electrons are transferred. Charges then on the atoms, maybe atoms are attracted because they have opposite charges. These ones in particular, though, in front of you are sharing electrons. Okay, we'll get into that a little bit later. But you can just think of it this way. You can think of it as carbon monoxide. Carbon has 12 protons, so it's kind of like this little tiny Lego that's got about 12. And oxygen has 16 protons. This has a little more than 16, but pretend it has 16. I couldn't find. And just like Legos, carbon monoxide, you can take 2 different atoms with 2 different properties, actually, in this case. You bond them together, and I guess you got to use this piece somehow differently. Carbon monoxide is very different than just carbon and oxygen, okay? So they have different chemical properties. Carbon monoxide, carbon dioxide, means I just got to go find another oxygen, another Lego piece, and then there's 2 of them. Okay, now you can't see them. All right, that's okay. Water is just 2 hydrogens and an oxygen bonded together, though, right? And that has to do more with sharing electrons. Hydrogen peroxide has these two oxygens once again, and then two hydrogens though, one on each oxygen, two oxygens, I should say. Okay, so we're talking about bonding. Concept check. How many of the following are considered elements as opposed to compounds? All right, so you have the H and the E. Big H, little e. That stands for helium. All right, we always have a capital letter, and that could be the abbreviation for an atom. And sometimes we have a lowercase letter right next to it, snuggled up close. So if we do, that HE combination stands for one type of element, the element of helium, right? That we fill the balloons with. Makes your voice funny. It's a gas. It's fun. The capital letter F, that stands for fluorine. And if there's two fluorine linked and bonded together, that's usually pretty typical for fluorine gas. Okay, so, but it's just fluorine. All right, helium, just helium. Now the next little guy over here is a capital H and a capital C, two different types of elements. Capital H is hydrogen, okay? Capital C with a lowercase l, by the way, that's a lowercase. That is actually chlorine. So you have one atom of hydrogen, one atom of chlorine bonded together to make a compound. Okay, so that's what is the compound. And then over here is sulfur, and there's 8 of them, but they're bonded, but they're just sulfur. Okay, so we might just call that sulfur and elemental sulfur. Okay, so yeah, how many? The answer is D, 3. Okay, I guess there was A, B, C, and D. 3 of these, and the elements would be helium, fluorine, and sulfur. There we go. Clue, a compound has a chemical formula with 2 or more element symbols. All right, so we kind of went over that. The first one's always capital, and if there's a second little compadre, it's lowercase and it's to the right and it goes with that capital letter. Cool, cool, cool. All right, so matter can be in different states, all right? It doesn't change the chemical nature, it just kind of means like different kind of energy. So yeah, I have different states. In the morning, I might be more energetic. At nighttime, definitely gonna be staying in my bed. Hopefully sleep. Okay, so I have less energy, I guess, in my bed, and I would be more like a solid. In this case, this is water, and it's got such low energy that the water molecules they like sit next to each other, and they're very rigid. And water is a solid. That's what gives it its solid shape. So you can't just pass your hand through ice unless you have superpowers. Okay, but when ice, we'll just call it ice, gets heated up, we'll call it water, and it gets more energy from the heat, and the molecules are more likely to be more slidey and slippery and liquidy, so that you could pass your hand through it. There'd be a little more give to it. Okay, not necessarily more space, just more give. They'll be like, all right, we're sliding, we're letting the hand go through. All right, so add a little more heat to it, and whammo, the water's like, hey, I'm not sticking around here. I don't want to stick around you guys. I'm going on my own. And they just fly off. And that happens. Even with just water sitting out the surface of the water, some of the molecules will get enough energy to overcome their friendliness for each other and sort of like, tendency to hang out, and they will just become water vapor or steam. Okay, which is a type of gas. Okay, so we have solid, liquid, and gas. We might give water a funny name when it's in its solid form. It's called ice, and it can make some pretty ice crystals and snowflakes because it like leaks together delicately in the air, and it's beautiful, but it's still just water, and you just melt it and get the water back. So that's how you can tell that there's no chemical reaction. We haven't broken any bonds. We haven't changed anything. Water's water. You could get water from the air, like the moisture harvesters on Luke Skywalker's little planet they started out with. So solid, rigid, with a definite shape, right? The ice cube, unless it's melting, the ice cube has its own shape, and it has a volume. So it's a set. Liquid has a definite volume, but it takes the shape of the container. You can just see, like, it's so slidey, it just fills whatever. Okay. Gas takes the shape of the container and its volume. It spreads out as much as it can, and it wants to spread out to the far reaches, and actually kind of wants to be even and equal all over the place. Okay. We'll go back to gases in another chapter. All right. So we did matter and solid, liquid, gas. And now we're going to distinguish between physical and chemical properties, as well as physical and chemical changes. Okay, so physical, chemical properties and changes. Matter's going to have both kind of like a physical, like how it acts, and then how it reacts, like breaking bonds. How's that gonna work? Like what happens when you break a bond of that type of atom combination, or how it happens if you join two different types of atoms? What's its new chemical that you're going to make? So chemical properties are described as substance ability to change into different substance. Okay, so if we were taking water, for example, that's the H2O, or let's stick with this one since I have CO2. Okay, if you broke off one of the oxygens, you're going to get carbon monoxide, which is poisonous. Carbon dioxide, not poisonous. Carbon monoxide, poisonous, and oxygen free radical, which can be dangerous. All right, maybe you broke them both, you can get some energy release probably in breaking the bonds. Maybe these two oxygen atoms would bind together and they become oxygen gas, and then here's just carbon, like a lump of coal, carbon. And yeah, so they have different properties when they're not bonded. To break bonds or to make bonds is going to create a different chemical substance, so we call that a chemical change. You may be familiar with some chemical changes that you've seen. Anytime something burns, yep, it's releasing the energy, and that's why you got the fire. That's why fire exists. This is a release of energy. Rusting, that's just combining with oxygen. So something, let's say it was some iron, pretend this is iron, and it combined with oxygen, and maybe there's like more than multiple irons, in one little group, but it's very different than regular iron. Regular iron doesn't have that red color, so it's a color change. Also, iron's a little firmer when it's iron. When it's rust, you can like poke your hand through side of a car that's rusty. Don't want to cut yourself because then you get tetanus. But yeah, these are kind of different examples of a chemical reaction. Anytime you're cooking, you're kind of changing the batter. The batter tastes funny before you cook it because actually you're causing some chemical bonds to be broken and some gas to be released and make that cake a little fluffy. So physical properties are the characteristics that don't involve changing the substance. No breaking of bonds or making of bonds. So the stuff stays the stuff. Okay. For example, the size, the shape, and the color. So if you have oxygen gas and you just like take out energy, right? You deep freeze it. Yeah, take a lot of energy. You can take oxygen gas and you can turn it into a liquid. You'll just take the energy from the molecules so that they don't want to spread out so far, and then they kind of huddle together for warmth. So yeah, liquid oxygen is what you're going to get, and then it's just a different state of matter, right? And then it's going to have a different size. Like liquid's going to take up less space because it's not flying around. May have a different, maybe a different color because you can see the oxygen liquid, so it's going to diffract light a little bit. Generally, though, permanent color changes are usually a chemical change. So I think like that, like acid indicator. When you dip something in acid, then it might turn pink, and that's a permanent change. But yeah, you take some gold and you hammer it out into sheets, still gold. It's just you change the shape of it. If you take copper and you string it into copper wires, then yay, it's copper wire, but it's still copper. You know what I'm saying? You melt it, it's liquid copper, but still copper. All right. If we oxidized copper and we added it to oxygen, it should be like copper oxide, it's going to be way different. It's not going to act like copper anymore. It's not going to conduct electricity like copper wires do. It'll be a little different. If you have it in a solution of water, it's going to be different that way. So a question to you would be, well, is dissolving salt in water a physical change or a chemical change? So you're taking solid salt, you stick it in the water still tastes salty, but the salt's not solid anymore. Yeah, the question you have to ask yourself is, can you get the salt back out of the water? Okay, so maybe you can do this experiment at home. You put salt in water, dissolve it so you don't see any more little chunks of salt, so don't add too much salt. And maybe you can heat up the water so more of it dissolves, because then it's got more energy, and it kind of like goes, hey guys, come on, break it up, and it breaks up the sodium chloride salt. But if you leave it sit out for a long time, a few days, the water evaporates, and what's left in your cup? hopefully some pretty salt crystals. So yeah, you didn't actually physically change the salt and where it was and dissolving it in that way, but it's still chemically salt, and you're going to get your salt back out. No problem. You can even cook with it still. All right. So physical chemical properties and changes. In that, matter undergoes like a physical change. If it does, we call it melting from solid to liquid, boiling from liquid to gas. Okay. Now, I think that if you're going from gas to liquid, we call that condensation, like in your windshield in the wintertime. If you get condensation in there because the moisture from your breath gets on the cold window and it like condenses to from water in the air to water on your windshield. Yeah, that's just a physical change. And then if you go from a solid or from a liquid to a solid, that happens usually more like in caves. We would call it freezing for water, but in other circles and other like chemicals, we might not call that. Well, I guess you might call it freezing still. Yeah, let's call it freezing. But the weird one is if you can go from gas to solid. Okay, that one's called deposition. That's the weird one. Like you're depositing money in your bank and your money's no longer gaseous. It's solid. It's in the bank. Okay. A chemical change now transforms the substance into one or more new substances. Okay. Or it might transform two substances into one new substance. Like if you took water, that's your two hydrogens and oxygens, and you put electric current through it, yeah, you're going to get free hydrogens is with hydrogens and free oxygens. Okay. Which is fine, I guess. And you're not going to be able to get them back easily. So that's the key. Chemical change, you can't just get it right back. You can't get water back from hydrogen and oxygen. You got to do weird things. So chemical change signs could be permanent color change, heat and light being given off. So any kind of burning reaction, heat absorbed, like, if you take those ice packs, if you like get hurt and you crinkle the ice pack, you're going to mix chemicals together, shake it up. They all mix. Maybe the heat's going to get absorbed from the outside. So that could be, so heat could be given off or absorbed. Lots of bubbles, which means you're releasing gas. So you've already had those molecules break off. The bonds were broken and then the molecules were released. That's different than when you're drinking your soda and the bubbles are bubbling up, right? Soda pop just has carbon dioxide dissolved in there, It's just escaping. It's not changing its chemical bonds. All right, and yeah, maybe new substance appears, like their solid suddenly appears in your little chemical reaction. Okay, that's different than when you're evaporating all the water out and then there's just salt left. Yeah, so maybe these are mostly what you would see when you see a chemical reaction. You probably know, at least you know a chemical reaction has occurred. Okay, let's watch this real fast. Okay, super great. All right, so is that a chemical reaction or is that a physical reaction? All right, what do you think? Was it a permanent change? Was it just a temporary change? And I don't know. Yeah, it's permanent change. Yeah, in color. Yeah, and usually it just indicates that there's an indicator in there that turns pink in the presence of acid. There wasn't acid before. Now there's enough acid. So that's that indicator changes physically from one type of chemical to another in the presence of acid. So that's kind of weird. All right, so next. It says you write your answer here, but it's okay. We're good. Oh. Okay, so hopefully we'll get to the next little slide here. My slidey thing is covered up. There we go. So concept check. check mark this items that are examples of a chemical change. Okay, now chemical change, getting a new chemical. Pulverizing or crushing rock salt. Bam, bam, bam. Is it still rock salt? Does it still taste like rock salt? Probably not a chemical change. Burning of wood. You're not going to get the wood back out. It's gone. It's burned. Boiling of water. Well, your water's going to go, but if you captured it on the lid, it would be back in liquid form, and then you'd be able to capture it. You just can't capture it from the air. It's still water. It's just fast moving water. Melting a popsicle on a warm summer day. Technically, the concrete does still taste like popsicle if you melt your popsicle on a concrete. Don't ask me how I know. So that's sad, though. You want the popsicle in your mouth. So maybe the popsicle melted in your mouth. Okay, but here's another thing. I want you to think about when you're eating something. The food goes in. Is the food changed? A little bit. When the food goes out, it sure doesn't look the same when it comes back in. It doesn't taste the same either. Yes. So you do chemical changes in your body to your food. So any type of cell, any type of living organism that eats and like uses food and nutrients, and it breaks it down and changes it chemically. So that's a chemical reaction. Any type of bacteria, yeast in bread, as it's growing, if anything to do with metabolism and growing, that's a chemical change. All right. So if there's biological things involved, you know that they make and take apart and build molecules to build you. All right. So your chemical change. All right. So hopefully you can learn to distinguish between mixtures, pure substances. We're going to do also 2 methods of separating mixtures. All right. So matter, you got different types of atoms here. As you can see with colors, the gold colors are gold, the copper atoms are copper, and the silver ones are silver. Okay, so we're just showing that when you melt down different atoms of metals and they're just snuggled real close to each other, they're not actually bonded. They just stay there until you melt them and separate them back out. Okay, so they call this an alloy because somebody decided to call that an alloy. It changes the property. So yeah, you don't want a gold ring. That's 24 karat gold. It's too soft. But if you mix in, some other types like nickel and other types of atoms in there, it's going to change. It's going to make the ring a little stiffer. You could still get your gold atoms out though. That's why it's not a chemical change. All right, you can still melt it out. Learn how to separate the silver from the dross or the gold from the nickel or whatever's in there. Okay, silver's a little less flimsy. All right, so this is mixture. So yeah, it's not a pure substance. All right, mixtures have a variable composition. In other words, they're saying that we have one type of atom bonded together, and then we got some other weird ones with it, okay, that are not the same combination of atoms. If you just had these guys together, that would be that wouldn't be a mixture. It would just be a pure substance. What did we decide this was? Little rusted iron or something, iron oxide. All right, so they're all iron oxide molecules. Think of this on a huge scale. But as soon as you mix something else in there, they're not bonded. They're just sitting next to it. We call it a mixture, and you're like, okay, that's duh. But people don't realize this sort of thing. Say you dilute something, you put water in your tea. Or you make tea. That's, what do you think? Mixture of pure substance. Got stuff in it, right? Well, technically, you could evaporate the water out and get the tea back. Yeah, get the tea back out. So this could, but when you're looking at your tea, unless your tea has chunks in the bottom, it should be well mixed. We call that homogenous. So homogenous is the same throughout. A hetero means different. Heterogeneous mixture has different properties in different parts of the mixture. So it's kind of more like a mud pie. Like there's water and you can see it dripping out, and there's mud. Some other examples could just be poorly mixed mixtures. If you let it sit, they separate out like oil and water. But a homogeneous mixture is, even if you set it on your countertop, you're not going to see all the particles floating around. How about pop? How about sparkly pop? Are you seeing your sparkly carbon? Yeah, that's not gonna stay in there. It's gonna be a heterogeneous mixture, not homogeneous. Okay, so maybe we know the difference here. Concept check. Label homogeneous or heterogeneous. Okay, pure water. What do you think? Homogeneous, heterogeneous. Is it the same throughout? It's pure. Nothing floating in there? Okay. Yeah, homogeneous. So that'd be an A. Gasoline. As far as I've seen, it just looks like gasoline. You don't see anything floating in it. You don't see any other bits. A jar of jelly beans. Lots of different things in there. Oh, lots of different color flavors. And you're like, but if we had the same jelly bean, some of them have speckles. That would not be well mixed. Okay. Just gonna go with, we're gonna assume they're the speckled type or like all different types of jelly beans. Soil. In soil, can you see like little particles of the vermiculite in there and some other like pieces of different types of soil or humus, the humus in there that is going to make it like retain moisture. Yeah, it's definitely not homogeneous there. So it's heterogeneous. Hetero means different. Homogeneous, same. Copper metal, pretty homogeneous, huh? Okay, good job. Now, if it was also like bronze, which is a mixture of copper and tin, maybe also copper and nickel, that's actually homogeneous, unless you can see chunks of copper and chunks of nickel. Most alloys are homogeneous. There we go. And in this case, we went a step further and said, look, copper metal is elemental. Doesn't have, in this case, anything else mixed with it. And it's not even a mixture. It's a pure substance, right? Water's pure substance, but it's got hydrogen atoms and oxygen atoms. So we're going to call it a compound, like a compound word. Two pieces of words put together to make one word. All right. The jar of jelly beans, yeah, if it's different colors. Okay, this one was saying if it's different colors, it's B. If it's not, they're going to assume it's heterogeneous. Okay, fine. Pure substance always has the same composition. Pure substances are of two types: elements which cannot be broken down into chemically simpler substances, and compounds, or could be compounds, which can be broken down, but may not be. All right, so pure, you have one type of element, all those atoms, nothing else. Okay, so like elemental iron, elemental oxygen gas, or you can have a compound where you have like maybe air. So, or sorry, compound, not air, water that has H2O with different particles. Okay, so a mixture would be neither one of these. It's not a pure substance at all. Mixtures could be air. Air is a very good mixture. And if you're thinking of clouds, though, then it's probably not very homogeneous because clouds are visible. So it's not well mixed if you're thinking all the air, all the atmosphere, okay? So we're thinking air, like what's in air, you're asking? Okay. Nitrogen, 77%. Oxygen, 21%. And the rest, like, a couple percentages of carbon dioxide, 3% probably. And maybe some xenon, radon, titrated helium. Yeah, there's all these gases in there, mostly nitrogen, huh? We don't get nitrogen inside us very much. We just don't absorb it, but some plants do. So let's try to separate mixtures. Okay, you could separate the air. Some means to separate substances that are mixtures would be distillation, kind of what we're talking about, where you boil something and you collect the vapor, you collect the gas, and then the gas kind of sort of runs downhill and then into this other container. And you call it a condenser because it kind of cools it quickly so that it doesn't just go up to the air. It actually turns it back to liquid. And then maybe you'll get your salt back out, or you can take ocean water and get salt from it. So that's how some people used to, in the old days, get some of their salt if they couldn't find it in the soil. Here is filtration. So it's kind of like making coffee, except for this time you put the grounds with the coffee or with the water, and then you just dump it through the filter. That's a type of making coffee. Usually they make it like drip, yeah, so you're going to need a good filter. The solid should get trapped in the filter, but the rest of the stuff that's in the liquid state is going to go all the way through. So that's how you separate a solid and a liquid, is filter. So matter, the things that matter, you can have pure substances, or you can have mixtures. Oh no. You can have mixtures, and you have homogeneous mixtures or heterogeneous mixtures, well mixed and not well mixed. That's all that says. And they could separate it by physical means into a pure substance. But pure substances like H2O and carbon monoxide, chemically, we could separate those. So those are compounds, all right? But the elements, if you have a pure substance of oxygen, it's just your pure substance is elemental oxygen, and you don't need to separate that, all right? But if your pure substance is water or hydrogen peroxide, pure hydrogen peroxide, not the stuff you get at the store, trust me, then you could separate it into its elements, hydrogen and oxygen. Okay, so that's cool. Label each type of matter with all that apply. Element, you put E there apparently. Compound with a C. Homogeneous mixture with a humana. Heterogeneous with a hem. Okay, cereal with milk. You see the cereal? You see the milk? Yeah, definitely not homogeneous. It's heterogeneous. Salt water. It's got the salt in the water, and those are not bonded together. They're just, you can separate them out easily. So we're going to call that a homogeneous mixture, I hope, because, unless you got too much salt. So assuming we say salt water, we mean just the water, just enough to make the salt dissolve. There's no extra salt floating around, because that would be saturated if it had a lot of salt dissolved. Gatorade. Is there anything floating in your Gatorade? I hope not, unless there's backwash. Should be a homogeneous mixture. Yeah, homogenized milk. Now this one's a misnomer because it says it's homogenized, but you let it sit, that top surface is going to have some milk fat in there, especially if it's 4% whole milk, So homogenized milk, well, it's just milk, all right? And milk is not well mixed mixture, because what's in milk? Oh, the fat, that's why you have the 4%, the 2%, and 1%, sure. Does milk have water in it? Yeah, that's what provides the wateriness. So we got some fat, some water. Some people are lactose intolerant, so milk has, yep, you guessed it, lactose, and it's a type of sugar. And then there's also some protein in milk, and that's the casein. That's what I'm allergic to. It's supposed to be good for you, though. Protein, yay. There's also some vitamins in there. So it's a mixture, but I'm going to say it's not homogeneous because that's why they had to homogenize it. They're trying to mix it enough so that when you go to gulp your milk, you don't gulp chunks of milk fat and stuff. But yeah, if you let milk sit around and curdle, yeah, it's not homogeneous. Okay, oil and vinegar salad dressing. You see, they don't mix so well. You're gonna shake it up, and you're like, oh, quick, put it on my salad. You try to homogenize it, but it's not really homogeneous. Make sure it's heterogeneous, right? The atmosphere. We just talked about that. You got clouds. I mean, if you're considering the whole atmosphere, no, it's not homogeneous. But if it's just the atmosphere in this room, the atmosphere in this room is just exciting with all this learning. It's pretty homogeneous. I'm not seeing chunks of nitrogen floating around and stuff like that. If there's fire, though, which lately there has been, that's not very homogeneous. So, yeah, I would say mostly we could say, no, it's not homogeneous. I don't see any elements in here. Pure elements. All right, if it said sodium chloride, that would be a compound, a pure substance, but it'd be a compound. Chlorine gas would be the element if it was just a bunch of chlorine gas. Sorry, we just didn't put any of those on here. All right, so congratulations. Y'all did great, and I hope that helps you remember some of this.